Welcome to the presentation of our published work in TAP entitled as a D-band wideband magnetoelectric dipole array based on micrometal additive manufacturing. It's a great honor for me to share this work for the APS community. I'm Zhong from Zhong University. Please feel free to contact us if you have any suggestions for this work. The first part is background and motivation. Nowadays, there has been noticeable development for subterranean applications, such as super-fast wireless link system, high-resolution imaging sensing, and centimeter-level positioning. At RF front-end, a wideband, high-gain, and high-efficiency antenna with a compact geometry is of great requirement. In the literature, planar substrate integrated arrays operating above 100 GHz have been reported. They have the advantages of wide bandwidth and compact fluence. However, the dielectric losses of these arrays are relatively high, leading to low gain and low efficiency. To overcome this issue, waveguide-based metallic arrays are used. The enhancement of gains and efficiencies comes from the low-loss field networks based on waveguides. As for radiating elements, slots and holes are widely used. However, the slots suffer from narrow bandwidths and the holes have high profiles. To fully address the antenna requirement for subterranean band, a new solution comes from new technology. We have proposed a novel wideband magnetoelectric dipole array based on micrometal additive manufacturing to achieve both wideband and high-gain performance in a low-profile geometry. Here is a proposed ME dipole antenna based on M and N. The middle shows the geometry of the antenna element. Here are some highlights. The proposed antenna is designed according to the fabrication process of MM technology and covers the whole D-band. The fabrication details are shown on the left. As seen in the right figure, a direct structure based on arm seal is developed to effectively excite the ME dipole antenna. Moreover, a throat cavity around the ME dipole antenna is used to enhance antenna gain and impedance bandwidth simultaneously. The design process and analysis are shown here. Antenna 1 has no cavity, antenna 2 is backed by a full cavity based on antenna 1, and the full cavity of the proposed antenna is slotted on two sides. We have simulated the S11 and the prosthetic gains of these three antennas. It's observed that there are two resonant frequencies in the opening band of each antenna. For antenna 1, the gain is reduced significantly at lower frequency, and the matching is poor. When the full cavity is loaded in antenna 2, in-band gain is remarkably increased, while the bandwidth is still narrow. For a proposed antenna, high gain and wide bandwidth are both achieved. To better ascertain the antenna performance, parametric studies are then carried out. It's briefly concluded that the resonance can be fine-tuned by inner and outer patch width. Also, the slotted depth is important for bandwidth improvement. Based on the proposed ME dipole element, an 8x8 ME dipole antenna array with arm seal field network is designed, whose geometry is shown on the left. For measurements, a waveguide arm seal transition is used as input port. The field network is to provide uniform power distribution and magnetic support for the antenna elements. The performance of the field network indicates wide bandwidth and no insertion loss. The proposed ME dipole array has been fabricated and measured. The measurement agrees well with the simulation. The impedance bandwidth of the proposed array covers the whole D-band. The measured prosthetic gain is up to 25.6 dBi. The simulated antenna efficiency is above 70%, and the measured average efficiency is up to 72.1%. The far-field measurement shows that the radiation pattern of the proposed array is symmetrical at both E and H planes. The side lobe and the back lobe levels are low. The cross-polarization is below -27 dB. The performance matrix is compared with the state-of-the-art, taking advantages of the proposed elements and wideband arm seal field network. The 8x8 ME dipole array has the widest impedance bandwidth among all the reported works. Also, with the planning configuration of the proposed ME dipole antenna, this work has the lowest profile compared to other arrays. Thank you for watching.